Hi, everybody. My name is Mike Schaekermann. I am a research scientist at Google Research. And today I'm excited to talk to you about AMIE, a research AI system for diagnostic, medical reasoning, and conversations that we've been developing here at Google Research and Google DeepMind. As I'm sure this particular audience is probably extremely well aware, there has been tremendous interest in applying artificial intelligence to medicine and healthcare settings over the last few years, and that interest really spans across industrial research labs and academic research labs. And especially with advances over the last 5 to 10 years in deep learning, such as convolutional neural networks, I think we've seen the rise of a plethora of promising applications in healthcare. A few examples from Google Research alone include reaching expert-level machine learning performance at tasks like breast cancer detection, skin condition classification, but also working on things like accurate deep learning-based variant calling for genomics. Now, all this is really promising, I think, but the reality really has been that translation of these independent point solutions, so to say, into real-world clinical impact has been rather slow. And some of this stems from the fact that the way that these traditional deep learning-based medical AI solutions communicate is typically in a very structured and fairly rigid format from a human's point of view. For example, a machine learning classifier might produce a categorical classification label for breast cancer present or not present, and that might be potentially accompanied with confidence information such as the sort of confidence level of the presence of a breast cancer. However, that kind of information would not allow the user to ask follow-up questions that could enable a deeper understanding, richer interaction, and ultimately lead to a trust-based relationship between human and AI. In short, traditional models and humans don't quite yet speak the same language. Now, luckily, while all of this progress at the intersection of AI and medicine specifically has been happening over the last few years, we've also seen another major revolution more in the technical side of machine learning around so-called foundation models, which I'm sure you're all well aware of, but just as a quick summary for those who might not be. The way that I like to think about foundation models is that these are basically very large-scale models that are trained on extremely large data sets with large computational resources, and often using something called self-supervised learning objectives. Some well-known examples of these models include BERT from many years ago, various versions of GPT, or over the last few years, first Google's T5 model, the PaLM model, and now more recently, the family of Gemini models. Now, the nice thing about these foundation models, as we all know, is A, they can be adapted to a wide range of downstream applications, including healthcare, and B, as one of the many emergent capabilities when fine-tuning foundation models the right way is that they can engage in coherent multi-turn dialogue using natural language. And these two benefits presented a great opportunity for our teams here at Google Research and Google DeepMind to really explore the art of the possible for conversational AI in medicine. And here I think I should pause and just emphasize that the physician-patient conversation is a cornerstone in medicine. An effective conversation between patients and physicians can drive accurate diagnosis, management planning, and empathy and trust between the patient and the physician. But it requires highly skilled and intentional communication, which is something that physicians really learn over the course of many, many years, spanning from their early days in medical school over their residency, but really throughout their entire career. Now, AI systems that are capable of such diagnostic dialogues could increase the availability, accessibility, quality, and consistency of care by being useful conversational partners to clinicians and patients alike. But approximating clinicians' considerable expertise and teaching a machine to do this kind of task has been a grand challenge for a long time. And that's where AMIE comes in, which is the topic of our talk today. AMIE stands for Articulate Medical Intelligence Explorer. It is a research AI system that is based on large language models and that is tuned for diagnostic reasoning and dialogue. We have optimized AMIE for diagnostic conversations such that it can ask questions that help it to increase its confidence in the correct diagnosis, while incorporating very important requirements of effective clinical communication, such as empathy, fostering a relationship, and providing information in a clear way. Just for an overview, AMIE uses a novel learning environment that leverages something we refer to as self-play and simulated dialogues to improve the quality of its own ability to produce diagnostic dialogues across a multitude of disease conditions, specialties, and patient contexts. And I'll go a little bit more into sort of another level of detail here, and we'll sort of provide a bit more in-depth overview of the system design that we leveraged for AMIE's development. We trained AMIE on real-world data sets comprising medical reasoning, medical summarization, and real-world clinical conversation data. And now it is feasible to train large language models using real-world dialogues that are developed by passively collecting and then transcribing in-person clinical visits. However, two substantial challenges limit the effectiveness of these real-world dialogues in training LLMs for medical conversations. First, existing real-world data often simply fails to capture the vast range of medical conditions and scenarios, and that hinders the scalability and comprehensiveness of the approach. And second, the data derived from real-world dialogue transcripts tends to be a bit noisy and contains ambiguous language like slang or jargon, humor, sarcasm, but also just interruptions that happen in the natural flow of like a verbal in-person interaction. It could include ungrammatical utterances, implicit references, and so on. And so to address these limitations, we designed a self-play-based simulated learning environment with automated feedback mechanisms for diagnostic medical dialogue that's situated in sort of what you can think of as a virtual care setting. And that really enabled us to scale AMIE's knowledge and capabilities across many medical conditions and contexts. And we've used this environment to iteratively fine-tune AMIE with an evolving set of simulated dialogues in addition to this static corpus of real-world data that I mentioned in the beginning. And further, we also employed an inference time so-called chain of reasoning strategy, which enabled AMIE to progressively refine its response conditioned on the current conversation to arrive at an informed and grounded reply when sort of not during the training phase, but when used during an actual conversation at inference time. Now, besides developing and optimizing AI systems themselves for diagnostic conversations, how to assess systems like that has also been an open question. And we chose to evaluate AMIE in a similar way that medical students in the real world are evaluated in many countries around the globe. And for that, we designed a study that was inspired by a standard format for assessing medical students. That's called Objective Structured Clinical Examination, or short OSCE. It's a bit of a mouthful, but I'll walk you through what that really is. You can think of OSCE as a set of multiple stations that you, as a medical student during exam time, might rotate through. And at each station, you are confronted with a human actor whose job it is to portray a certain medical condition based on a script that that actor is given. Okay, and it is your job as a medical student being examined to interview the patient, take their history, and then generate a diagnosis and treatment plan. In our study, we simulated such an OSCE using text-based conversations and compared AMIE's performance to that of primary care physicians in a randomized double-blinded manner. The so-called ingredients for this study were 149 case scenarios. That's the script that the patient actor is given. And those stemmed from clinical providers in Canada, the UK, and India. It also included 20 primary care physicians for comparison with AMIE. And finally, evaluations by specialist physicians and patient actors. And I just want to call out that this group of specialist physicians was separate from the primary care physicians that AMIE was being compared against. Okay, I'll just walk you through a bit more detail of what happened in the study for each of these scenarios that were under investigation. The study consisted of 3 steps for each simulated patient. And a simulated patient in this context refers to sort of the combination of a scenario pack and a patient actor that portrays that scenario pack with the script of this mock patient case. Okay, so in the first step, the simulated patient interacted with either the primary care physician or the human doc, or with AMIE, our AI system, using a synchronous text chat interface and portrayed their condition that was specified in that scenario pack. And this assignment of simulated patient to either AI or human PCP was randomized and blinded, meaning that the patient actors were not really told whether they were interacting with a bot or a human. Second, both the patient actor as well as the chatbot were asked to fill out a short questionnaire after completing the text chat. And here I said chatbot, sort of quote unquote, which refers to either the human doctor chatbot or the AMIE AI chatbot. And for patient actors, which is here on the left side, patient actors were asked to reflect about how they perceived the conversation from more of a patient's perspective. And that included aspects like relationship fostering, perceived empathy, but also other things. And the doctors and AMIE on the other side, here on the right side, they respectively were asked to provide a differential diagnosis as well as investigation and treatment options and recommendations for escalation and follow-up, given the consultation transcript that they had just generated in conjunction with or in collaboration with the patient actor. And finally, in the study, we asked a separate pool of specialist physicians to independently assess the quality of the consultation transcript and the assessments that were made by the human doctors or AMIE after completing the conversation. And these evaluation axes that we used in the study were inspired by well-accepted tools that are used in the real world to measure consultation quality and clinical communication skills. And those were chosen to probe for abilities around history taking, diagnostic accuracy, clinical management, but also clinical communication skills, including relationship fostering and empathy. And next, I'll walk you through some of the results from our study. So first and foremost, AMIE's differential diagnoses were assessed by specialists as being more accurate than those from human primary care physicians. And this was done by comparing the differential diagnoses from human doctors and AMIE with what was the sort of considered the ground truth diagnosis for each scenario, and checking whether there was a match of each item on the differential diagnosis list with that ground truth diagnosis from the scenario. And the graph that you see here shows that no matter whether we looked at just only the top item on the differential list or at the entire differential diagnosis list, which might have contained up to 10 items, AMIE was more accurate than our human doctors. And next, we looked a little bit more into what actually happened in the conversations and how much information was conveyed. And we found that although AMIE displayed greater verbosity compared to PCPs in terms of simply the total number of words generated in AMIE's responses during the consultation, the number of turns, so the number of messages exchanged, and the number of words that were collected and elicited from the patient actors were actually similar across both of these conditions between AMIE and the human doctor. And that really suggests that both AMIE and the human doctors acquired a similar amount of information from these patient actors during the encounter. Now, to investigate further whether AMIE's sort of significantly better performance at diagnostic reasoning stemmed either from better information acquisition or from better diagnostic reasoning capability per se, we compared AMIE's diagnoses based on its own consultation transcripts with AMIE's diagnoses that were generated based on the conversations that the human doctors had with the patient actors. And our results here revealed that the diagnostic performance of AMIE remained consistent regardless of whether AMIE processed information from its own dialogues or from the dialogues that were generated by human doctors. And I just want to pause here and highlight that this result suggests that AMIE was approximately equivalent to human doctors at information acquisition, but it was much better than human primary care physicians at interpreting that information to produce an accurate and a complete differential diagnosis. Now, switching gears a little bit to look at perceived conversation quality. From our specialist physician perspective, we had this pool of specialist physicians assess a total of 32 quality axes that probe for abilities around history taking, diagnostic accuracy, clinical management, communication skills, and so on. For the sake of simplicity and brevity here on this slide, I only show a subset of 6 of these 32 evaluation axes, so you get a rough idea of what the trend looked like and what kinds of axes we included. And in summary, we found that according to specialist physician assessments, AMIE outperformed human PCPs on 28 out of those 32 axes, while being comparable and not inferior on the remaining 4 axes. Now, switching perspectives and looking at those results from the patient actor's perspective, we actually got quite similar results. On 24 out of 26 axes, patient actors rated AMIE's conversations as higher quality than those from human doctors, and no significant differences could be detected for the remaining 2 axes. And here you will see, if you look at the different axes that I show on the slide, which again is just a subset of the 26, you will see that here from the patient actor's perspective, we probe for dimensions like perceived politeness, perceived sort of ability of making the patient feel at ease, explaining the condition and recommended treatment, involving the patient in treatment decisions. So overall, a set of axes that is more appropriate to be assessed from the patient actor's perspective, or in a real world setting would be assessed by a patient themselves. Now, in summary, I think it's fair to say that AMIE outperformed human primary care doctors on multiple evaluation axes based on our evaluation, and those included diagnostic accuracy and the quality of the management plan, but also the quality of communication skills, including aspects like perceived openness and empathy. And again, some of those aspects were rated by specialist physicians, such as the diagnostic accuracy, and some were rated by patient actors based on their interaction with AMIE or the human doctor. Now, finally, before I close, I want to highlight a few limitations of our research, which should inform how these results are interpreted. Namely, they should be interpreted with caution. Firstly, our evaluation technique likely underestimates the real-world value of human conversations, because the clinicians in our study were, as you know after this talk, they were limited to an unfamiliar text chat interface, which permits large-scale LLM patient interactions, but is not representative of usual clinical practice. Now, secondly, any research of this type must be seen as only a first exploratory step on a long journey. And transitioning from LLM research prototype that we evaluated here to a safe and robust tool that could be used by people and those who provide care for them in the real world will require significant additional research. And then finally, there are many important limitations to be addressed, including experimental performance under real-world constraints, like I just said, and a dedicated exploration of such important topics as health equity and fairness, privacy, robustness, and many more, to ensure the ultimate safety and reliability of the technology. Before I close, I want to make sure that I call out that I'm here speaking on behalf of many, many individuals that have contributed either directly to this work or have supported it in other ways. And I really just have the privilege to present this work on behalf of the group to this audience today. Thank you very much.